Dripping down science. The Naked Scientists.
Catching criminals and tackling terrorism. This week we're exploring two ways to sniff out concealed explosives and a new technique to lift fingerprints from surfaces that have been cleaned or burned. Hello, it's Sunday, June the 24th. I'm Helen Scales, and also here this week is Chris Smith.
Hello, and in the news this week, a new way to halt the degenerative brain condition Huntington's disease. Plus, what do you think of this? That music actually evolved from a much less mellifluous starting sound using the same principles of natural selection that control how species change. You can hear how Darwin Tunes, which is the website behind that tune, works very shortly.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
With the advent of global terrorism, it's become apparent that people will go to extreme lengths to conceal bombs. So quickly and accurately detecting trace amounts of explosives could not only save lives, but it could make air travel safer, quicker, and a lot more convenient. And now, researchers at St Andrews University have invented an explosive-detecting plastic that could be used at airports and even on minefields. Dr. Graham Turnbull is the inventor. He's with us. Hello, Graham.
Good evening.
So tell us, how did this work get started? Plastics to pull out explosives. I've heard of plastic explosives, but not the other way around.
No, we're using plastics to find explosives. So in St Andrews, we're developing a set of materials called organic semiconductors for a range of different applications in optoelectronics. Now, these materials are a special class of plastic that unusually can conduct electricity, which is an unusual property for a plastic, but also can be stimulated either by illuminating with light or by passing electricity through it to emit light. So these materials are now being used for a range of applications as plastic light-emitting diodes, in Samsung mobile phones, for plastic solar cells, for plastic lasers. But it turns out that the same set of materials can also be used as a sensor. And following on from some research by a group at MIT, we started to look and see how we could use our plastic lasers as very sensitive sensors for detecting explosives.
So what's the technique then? That the laser shines on the plastic and it changes the electrical activity of the plastic, but if the explosive is present, you get a different signal or something similar?
It's something along those lines. So essentially what our sensors are doing is they're replacing a sniffer dog's nose. So we operate our plastics by illuminating them with ultraviolet light, and then the plastic then re-emits that energy as visible light. Now, if we take a thin film of one of these light-emitting plastic materials, and we bring a small number of TNT molecules, or molecules similar to TNT, into contact with the film, the TNT molecules can interrupt this light emission process. Essentially, it switches off the light. So if there's explosives present in the atmosphere surrounding the plastic film, the light emission is switched off or made dimmer. If you blow clean air across the film, then the light emission returns. And so it's a reversible process that can detect the presence of very, very low concentrations of explosive molecules in the surrounding atmosphere around about the film.
How specific is it? Because you mentioned TNT, trinitrotoluene, the stuff that's in the majority of the 100 million or so landmines that we know are lurking out there somewhere around the world. But other explosives are used too, and people are getting cleverer and cleverer in terms of the explosive cocktails they'll use. So is it just TNT, or could it work with other chemicals as well?
As you say, TNT is the major component of all military high explosives. But also when you make TNT, you also fabricate other similar molecules like DNT, dinitrotoluene, instead of trinitrotoluene, and various analogues. This technique is able to detect a wide range of these nitroaromatic molecules. It also has potential to detect some of the other plastic explosive molecules. The process works on a difference in energy states between the light-emitting plastic and the explosive molecules, and essentially works by switching off the light emission by electrons hopping from the light-emitting plastic onto the explosive molecules. So it can detect a wide range of different materials. It doesn't intrinsically discriminate between those, but that's one of the sort of next steps that we're trying to look at to get selectivity.
What about the problem of selectivity? Because one of the big hold-ups at airports is that people might have something, their shampoo or something that triggers this agent, and in fact it's completely innocuous. So is there a false positivity with this? And if so, is that a problem, or is it at a level that is going to be tolerable?
I think with all sensing approaches, there's some danger of false positives. There are things that could be in your luggage that conceivably could trigger these things. So angina sprays contain trinitroglycerine in them in very small quantities. But in general, we believe that it's a workable solution. In a different context, in which we're interested in the area of landmine clearance, which has security implications as well, because there's in former war zones, there's a lot of explosives lying around that terrorists in principle could get their hands on, and so clearing landmines has a security benefit for the Western world.
How would the technique work though, Graham? I mean, what would you do? Would you have a box where some of the plastic being illuminated by the UV is in there, and it's being watched by a camera, for example, and a gas stream is pulled across your luggage or across the minefield, and that air then interacts with the plastic?
That's right. So that's the sort of the approach is that we take one of our little plastic lasers, which are postage stamp sized lasers, and you essentially can draw some of the air across the plastic film, the little polymer laser, and you then monitor the amount of light emission that is being emitted.
And so it is very portable. So the concept of mounting this on some kind of mobile device that could explore a minefield and find hotspots of the gas that could signify an explosive buried underground coming up, that's not beyond the realms of possibility. Not
at all. Our plastic lasers are very compact. Within a collaborative project in the UK called Hypix, we've been developing miniaturized compact versions of these plastic lasers, where essentially we take a high power light emitting diode, we remove the plastic dome lens and replace it with one of our plastic lasers, and so the actual source can be the size of an LED. In other work in the Hypix program, we've also been developing fluorescence based explosive sensors that are based on 2 silicon chips. So these are all laboratory prototypes, but they show a lot of promise for being able to make very compact sensors.
And relative to a sniffer dog's nose, where would your plastics sit? More sensitive, less sensitive, or about the same? And what's the absolute numbers in terms of parts per billion or so of the explosives that they can pick up?
So sniffer dogs' noses are regarded as the gold standard in sensitivity. I'm not sure I have a quantification for how low they can go in sensitivity. This sort of approach is the one that gives you the closest to the sniffer dog's nose in sensitivity. In the laboratory, we routinely do tests on new materials with parts per billion quantities of TNT in the air, and the technique can go much lower than that in terms of sensitivity.
But unlike a sniffer dog, I suppose your plastics won't get tired or need to play with a ball periodically to keep interested.
That's right. So a sniffer dog needs to be playing a game in order to detect explosives. In practice, depending on the environmental conditions the dog's working in, they may typically work for half an hour at a time. And so long repetitive searches, or if you want to go into very hazardous areas, there are problems with using dogs in those sorts of conditions, and so a high-tech alternative that doesn't get bored is an attractive possibility.
Graham, thank you very much. That's Graham Turnbull. He is from St Andrews University. He's with us for the rest of the programme. If you'd like to get in touch, you can tweet at Naked Scientists. You can also comment at facebook.com/TheNakedScientists, or emails operating too, chris@thenakedscientists.com.
Well, some substances, including drugs and explosives, can be concealed by dissolving them in another liquid, such as an innocent-looking bottle of spirits, or packaging them inside an opaque container. This makes it very hard for security or border forces to find them without having to open and potentially compromise the contents. But now, Cobalt Light Systems, a company spun out from research funded by the STFC, have developed a device that can see through packaging and tell you exactly what is inside, using a technique called spatially offset Raman spectroscopy, or SORS. Professor Pavel Matusek developed this technique at the Rutherford Appleton Laboratories near Oxford, and he's the Chief Scientific Officer at Cobalt Light Systems, and he joins us now. Hi Pavel, thanks for joining us.
Hi Helena.
Well, perhaps we should start off by saying, what is SORS, or can I call it SORS?
Yes, indeed, we do call it SORS.
SORS, OK. What is it, and how does it work?
So SORS is basically a laser spectroscopy technique. It's based around well-established technique called Raman spectroscopy, which provides a high chemical specificity or high ability in accurately determining the chemical composition of the substance we are probing, but with a twist. And that twist allows us to apply it to much wider range of containers, which then enables us to satisfy requirements of regulatory bodies for use of this technique at aviation security to determine the content of unopened bottles.
So what is it? And it's a type of laser light, is that right?
Indeed. So what we do, we shine a laser light onto a sample, similar to a laser pointer, but slightly higher power. And photons hit the sample, they scatter, most of them elastically, therefore they don't exchange energy with the material, but tiny fraction of these photons activate vibration within molecules they are hitting. And as a consequence, they lose the same amount of energy they used to activate the vibration motion, and then as a consequence of that loss of energy, they change color. And a single molecule can have a number of energies which it can accept. These are discrete, and therefore, if we examine the spectrum of the photons which are emitted back at us from a sample, look at the characteristic lines and different colors and their intensity pattern, we can determine as a fingerprint, using it as a fingerprint, what chemical component we are looking at. So this is the basis of the Raman spectroscopy technique. The twist we are using is that we are actually not collecting the signal from the zone which is illuminated by the laser light, which you would do in conventional Raman spectroscopy, which would result in you being dazzled by the surface of a sample you are probing, for example, the container wall, but probe several millimeters sideways. There we are seeing much more cleanly substance inside, and we are not overwhelmed by signal coming from the surface. This is a situation similar, for example, to the stars in the sky. At day, you don't see them because you are dazzled by the sun radiation. However, if you wait long enough for night, you can see stars clearly, or if you have a sun eclipse, you can see them clearly too. In a similar way, we are going sideways and suppressing, in effect, dazzling radiation coming from the surface.
So in a sense, you're being able to see through the container into what's inside it. How can you tell if something is actually dissolved in there, something that you're interested in, and that security people are interested in?
Well, we basically examine that spectrum, that pattern of lines which we are detecting, and that informs us about the content. If you have a mixture, you would see the content of a solvent and solute very clearly. So that's what we are doing. And we are comparing those fingerprints against the library, which holds prohibited substances, which could be explosives. And if explosive is found, we sound an alarm. The unique feature of this technique is that we reach extremely low false alarm rates. That means if you put a benign bottle into the system, false alarm rate can be sound in only 0.5% of cases, whereas conventional technology which is in existence would have these false alarm rates 10 times higher. Therefore, disruption to airport operators is much lower. This is a insignificant rate or false alarm rate, if you like.
So it's not going to set the alarms off when they shouldn't go off. But how sensitive is this as a technique? Will it actually detect, small quantities of the stuff that we're interested in?
It can certainly determine or detect the quantities which are relevant, because trace quantities dissolved in something are not significant. It can detect quantities maybe at a level of 0.5% or 0.1% or 1%, but those are concentrations which are relevant for explosives to be viable. And in security settings, this satisfies the requirements of the regulatory body. This instrument passed so-called ECAC test, which is a European test which is required for this type of technology to be deployed at airports with flying colours.
And is this sort of technology something that we will see soon? And is it quick enough that everyone can be tested, or is it going to be a case of still testing a sample of a number of people who come through security, or will it be sort of a routine thing that we will all have any liquid we have in our bags zapped by your machine and they will tell what's inside our bags?
The speed of the machine is adequate to test every bottle which is of significant amount of liquid, containing significant amount of liquid. Test itself takes 5 seconds. So idea is that you have an X-ray machine, and if X-ray machine identifies something suspected in your bag, you would take it out, put it inside the machine, and our machine would verify that the content is benign, or would sound alarm if there's an explosive found.
And presumably, if terrorists and people who are trying to get these things through come up with some new molecule that isn't in the database, then that's going to be a problem, and you'll have to keep up with the technology as that advances as well.
It's of course up to security authorities to maintain the library bases relevant to this. Indeed, you would have to update the database as you go along in order to have effective device or screening device.
Finally, will this mean that we'll be allowed to take more liquids with us on the plane in the future? No longer restricted to, is it 100 mils you're allowed now?
Indeed, at the moment it's 100 millilitres. The plan, anticipation is that this ban would be, or restriction would be lifted in April 2013, and we are expecting the final verdict on this by European Commission later this summer, whether this ban is going to be lifted in April or how it's going to be, whether it's going to be staged or 1 year later.
Well, we'll wait to find out. And I hope so, because I always end up having to drink all my water before I go through security. And
then you want the wee,
always a bad
don't
thing.
You, all the way through the flight.
Exactly. Thanks, Pavel. That's Professor Pavel Matusik from Cobalt Light Systems telling us all about SAWS.
Distilling the best science. The Naked Scientists.
You're listening to The Naked Scientists with Chris Smith and with Helen Scales. We'll return to our theme of catching criminals in just a moment, including looking at a new way to fingerprint surfaces that previously were considered unfingerprintable. But first, let's take a look at what's been making science headlines this week. I'm going to kick off with this one. They say that manners maketh man, but it looks like microbes maketh man, and any old bacterium won't do. To be healthy, an animal requires a unique consortium of microbes in its intestines, and this is according to scientists in the US this week. Now, you've probably heard of the hygiene hypothesis, this idea that if we live in an environment which is too sterile or too clean, then your immune system doesn't get exposed to the right doses of microorganisms, so you're more likely to develop allergies or autoimmunity. Now, this is partly based on observations that if you look in other animal species, and there's in fact a kind of squid, probably familiar to you, Helen, which if it doesn't team up with a relative of the cholera bacterium called Vibrio fischeri, then it doesn't have a light-emitting organ. It doesn't develop a tissue on its body that gives out light. Similarly, tsetse flies absolutely have to team up with a bacterium called Wrigglesworthia glossindia, which gives them vitamins, because if they don't make that association, they're infertile. So microbes can make a difference to the health of an organism. What about humans? And will any old muck do, or do you need certain kinds of bacteria like these two other species I've named? Well, there's a group at Harvard in the States. They've published in the journal Cell this week their attempt to answer this question. This is Dennis Kasper and his colleagues. What they've done is to take mice which have been born into a germ-free environment. In other words, you give a mouse a caesarean section and you get the babies and they're sterile via that route. You then infect one group of the baby mice with normal bacteria from normal mice, from their intestines. A second group, you do the equivalent using human intestinal bacteria. The third group you leave in that sterile environment in order to see how they perform as controls. What they found is that the mice given the mouse bacteria performed exactly as you would expect. They were perfectly healthy. The mice that got the human bacteria developed a flourishing, thriving community of microorganisms in their guts, but which very closely resembled what you would find in a human anyway. The thing was, though, that when they then looked at the immune systems of these mice, which were riddled with bacteria, they weren't right. And it turned out that they had far fewer lymphocytes. These are white blood cells that fight and regulate your immune response in the wall of their intestine, their intestinal lining. They had far fewer lymphocytes in the lymph nodes, the glands that present things to the immune system to regulate it. They had far fewer cells called dendritic cells that actually present things to the immune system to inspect. They made far fewer antibodies in their intestines, and they had far fewer of these defense proteins that they secrete across the wall of the intestine to keep microbes at bay. And when the researchers challenged their mice with a dose of Salmonella, the mice that had the normal mouse bacteria fought it off without too much problem. The ones that had the human bacteria succumbed to infection and were quite sick, and they were as sick, in fact, as the ones that were reared in a sterile environment. So the point they make in their paper is that actually it's not just having microbes and dirt. It appears to be having a very unique cross-section of microbes that you acquire probably from your parents when you're born. They are absolutely essential to develop a healthy immune response, not just any old bug.
I mean, presumably we could think about whether caesarean sections in humans means that babies sidestep this dose of bugs that could be potentially very important because they're not born in the normal way. Is there any evidence for that?
There is, actually. People have done a number of epidemiological studies, so this is known to be an association. It's not causal. We don't know, we can't prove it, but we can say there is an association between being born via caesarean section and having a higher risk of allergy later in life and a higher risk of diarrheal illnesses. And people have shown that babies that are born by caesarean acquire a different fingerprint of bacteria when they're first born. They pick up sort of hospital bugs and staph and streps and clostridia and things, compared with babies that emerge via the normal route get, as some researchers delicately put it, a mouthful of muck. And that mouthful of muck is their mum's muck, which is ideally suited actually to them because they're genetically very similar to their mum and they're going to exist in almost the same environment as their mother.
So muck can be good. Well, I've got a story now from the plant world, which is that scientists have discovered a new way that carnivorous plants catch their prey. And these ones use the power of raindrops to help flip insects into their traps. Well, tropical pitcher plants have evolved specially adapted leaves that form a deep bowl, partially filled with digestive fluids, and with a little lid that projects over the top to stop their plant from getting filled up with rainwater. Well, the plants produce nectar to attract insects, and they set various traps to catch them. The inner wall of many pitchers is covered in waxy crystals that become very slippery when they're wet, so the insects fall right in. Well, the pitcher plant Nepenthes gracilis is unusual because they also produce these crystals on the undersides of their lids. And researchers wondered whether the lid itself could be involved in helping to trap prey. Because if you think about it, an insect clinging to the underside of the lid is right over the trap and in a very precarious position indeed. Well, watching these plants in northern Borneo, Ulrika Bauer from the University of Cambridge and her team saw ants happily walking on the inside of this pitcher plant lid and not falling in. But then during a rain shower, they happened to spot a ladybird crawling underneath a pitcher plant lid to take shelter, only to be flicked by a raindrop into the trap. Well, to test whether lids really are helping to trap prey when it's raining, the team took some pitcher plants and some ants into the lab and doused them in showers of artificial rain. And they found that around 40% of the ants visiting the pitcher plant were caught when it was raining. And then when the rain was switched off, no ants fell into the trap, showing that it's not just that the lids are becoming more slippery because of increased humidity after it rains. They also performed the very same tests on picture lids cut off and mounted on a paperclip, and that gave them a similar result. They also went back into the field and added a smear of anti-slip silicone to the underside of these pitcher plant lids, and that also made them very much less efficient at catching prey in the rain. Well, the paper appears in the journal PLOS ONE, and it's accompanied by some video clips of the ants having a really tough time getting to grips with pitcher plants in the rain. And it really does seem that Nepenthes gracilis has evolved to be a lid specialist. They make more nectar in their lids than other pitcher plants, and the team also found that the crystals on their lids of this waxy stuff is actually a different microscopic structure than in other plants. It lets ants hang on in dry conditions, but the vibration of raindrops is enough to catapult them into those digestive juices. And it's thought, and this bit I really love, it's thought that basically the ants that escape when it's dry act as scouts. They go back to the colony and say, hey, I found this fantastic plant. They bring back lots more ants to these pitcher plants. And then because it's a very rainy part of the world, chances are that when all these ants come back, they could find that the heavens have opened and that the pitcher plant is actually a very much more dangerous place to be.
Isn't that incredible? Thank you, Helen. Are you a leader or are you a follower? An intriguing new study shows how you can identify influential people from their activities on Facebook. Sinan Aral is at the New York University Stern School of Business. He's with us now. Hello, Sinan.
Hi.
So, first of all, what were you trying to prove with this study?
Well, in essence, finding influencers, or as you said, influential people is sort of all the rage today. Companies like Klout are trying to measure influence scores for people in social networks like Facebook and Twitter. But beyond marketers, managers and policymakers are more generally interested in how behaviors spread through society. And in this paper, we present a general method for measuring influence and susceptibility in networks. And the main contribution of the method is that it avoids known biases in current methods such as homophily bias. Homophily means that we tend to make friends with people like ourselves. For example, if two friends adopt a product or a behavior, one right after the other, current methods have a hard time distinguishing whether it's because of peer influence, one friend influencing the other, or if friends simply have similar preferences and thus behave similarly.
And obviously the world doesn't work like that because an influential person isn't just influencing their friends. They have the ability to influence a range of different demographics.
Exactly. So what we did was we applied this general method to measure influence and susceptibility in the adoption of a commercial product on Facebook among 1.3 million users, and we were able to recover influence and susceptibility scores that aren't subject to these known biases like homophily bias.
Okay, so can you talk us through what you actually did? How did you recruit the people? And then what actually happened to discover this?
We worked with a company that developed a commercial movie application where you can rate movies and buy movie tickets and read about directors and actors. And as people adopted this application, we randomly assigned them to send messages to their friends in a random manner. So every time you did something on the application, like rate a movie or talk about a celebrity or something like that, it would randomly select a subset of your Facebook friends to send a message to. And this randomization removed the selection bias of people selecting friends with similar preferences or selecting people who they knew would be specifically susceptible to influence. And with this randomization, we were able to measure, for example, how your characteristics or your traits, your age, your gender, your relationship status on Facebook, or anything that we could observe about you on Facebook was correlated with your likelihood of responding positively and adopting this application upon receiving this influence-mediating message. And because the messages were randomized, we could make causal inferences about whether this message was causing you to adopt or not.
What about the other way around? Because that's looking at people, how they respond to receiving the message. What about in terms of the people who actually send the message? Are you inferring whether they're influential or not based on what the response of the recipients is?
Exactly. So we estimated a statistical model that estimated both influence and susceptibility simultaneously while these random messages were being sent to people from their friends.
So, spill the beans then. What makes someone highly influential? Is it just that they're very well connected, or is there something special? Is there some special recipe that means that if they say something on Facebook, everyone's going to be talking about it?
Yeah, in fact, we found that it's not just how many people you're connected to, and lots of people have been focused on that in the past, how many followers you have, but more importantly, it's whether you persuade your followers to change their behavior. And so what we found was that in the context of this particular movie application, when we applied this method, that men were more influential than women, that women influence men more than they influence other women, that older people are more influential and less susceptible to influence than younger people. Married people are the least susceptible to influence. And influence and susceptibility trade off, meaning people who are more influential tend not to be susceptible, and people who are susceptible tend not to be influential.
Isn't this just what we see in politics, though? If you take a look at the Houses of Parliament here in the UK, or you look at the Congress in America, do you not already see this playing out? We're just basically proving what we already know.
Not exactly. So it's not clear whether or not influential people should be more susceptible or whether older people should be more influential than younger people. And my intuition is that as we begin to apply this method across different behaviors and products, that we're going to see different types of influence emerging in different contexts. In a different context, it could be that women are more influential than men, or that younger people are more influential than older people, the opposite of what we find here. And the value of this paper is it provides a method to measure this in any context. And I'm really excited to see what we might find for other types of products or behaviors.
If we could just look at the question of the men and the women, do you think the fact that it was movies might have led you to conclude that men were more influential than women in this context? Do you think if you'd done something on a subject that women are regarded as more authority figures in, you'd have seen the flip side of the argument?
It very well could be true, absolutely. So you could imagine other contexts in which women might be more potentially influential than men. But this, in every context, is an empirical question. And the benefit of this measure is that we can now talk more scientifically, more rigorously about influence and susceptibility in a causal way.
And do you see this being applied to job interviews anytime soon, in the sense that you come for your job interview and someone decides they want management material, or they want someone who will be well trained and toe the line, and they subject you to this sort of analysis, and you can put people into those sorts of categories?
Yes, I think that it could certainly be applied to those types of situations, but I actually think it's much broader, and it's interesting for other types of questions as well. For instance, it's not only about targeted advertising or jobs. We're also now working on applying these same methods and the same science to promote HIV testing in Africa by trying to understand how we can use peer-to-peer influence to spread positive behaviors in society: diet, exercise, political awareness, and, like I said, HIV testing in South Africa.
Sinan, we must leave it there, but thank you for joining us and updating us on that. That's Professor Sinan Aral. He's from the Stern Business School at New York University, and that paper he was talking about was published this week in the journal Science. Now, also this week, scientists have come up with a way to potentially halt the fatal inherited degenerative brain condition known as Huntington's disease. This affects about 1 in 10,000 people. It causes a progressive loss both of cognitive abilities, but also causes movement problems and coordination problems and behavioural issues for people who are affected. And because it's transmitted genetically, it's present in all of your brain cells, and therefore it's not trivial to try to reverse the expression of the Huntington's gene, which appears to be critical to the function of the development of the brain in the first place. But what Don Cleveland and his colleagues at the University of California at San Diego have published in the journal Neuron this week is a way to switch off the expression of the gene in the brain in mice. They do it using RNA interference, which won a Nobel Prize for the people who discovered it about 5 or 10 years ago. And what they do is make a genetic mirror image sequence, an interfering RNA molecule, to a part of the gene responsible for causing Huntington's disease. This they then infuse into the fluid called the cerebrospinal fluid that bathes the brain. It then moves into the nerve cells in the brain, and because it binds to its mirror image genetic message in the cells, the Huntington's gene product, it effectively switches off the gene. And this has the effect of stopping the cells building up something called polyglutamine, because people with Huntington's disease have an abnormal amplification or duplication of a piece of genetic material containing 3 genetic letters, CAG, and this repetition many times in the gene causes the cells to make long molecules of something called polyglutamine, which they then can't break down, and this builds up with toxic effect inside the affected cells. And when Don Cleveland and his team used mice that carry the human gene for Huntington's disease and themselves develop abnormalities, when these animals were infused with this particular construct, they had a 75% reduction in the expression of the gene, and the other benefit was that the animals then showed behavioural improvements, movement improvements, and there was a long-term benefit, suggesting that if you only intervened periodically in this way, you could nonetheless stop the disease manifesting in people. They also showed that you could deliver the genetic construct via the same sort of cannula that you use to give a spinal or epidural anaesthesia to a person who is giving birth to a baby, and they demonstrated this with a monkey. So, very encouraging piece of work.
Yeah, good news there for the fight against Huntington's disease. Well, now with a roundup of other science stories hitting the headlines this week, including a camera that has 5 times the resolution of the human eye. Here's Mira Sinthilingham.
The H5N1 bird flu virus could evolve into a form that's transmissible in humans, according to research published in the journal Science. In this controversial project, Ron Fouchier from the Erasmus Medical Centre in the Netherlands infected ferrets with versions of the virus that were genetically modified to increase their affinity to mammalian cells, and monitored how the virus continued to mutate upon infection. The team found that just 5 mutations in total were enough for an airborne and transmissible strain of the virus to develop.
Many of the mutations that we have introduced with genetic modification are already found in the field. So it's now a matter of chance of a mammal running into a chicken that has a virus with those mutations. And then in that mammal, it can accumulate the extra mutations, and then we would be in trouble. Many scientists believe that only H1, H2, and H3 viruses can cause pandemics rather than H5, and many scientists think that it has to involve pigs. And this investigation really showed that we should not be so relaxed.
A 50,000 megapixel camera has been created by scientists at Duke University in the US. The camera uses an array of 98 microcameras within a spherical lens, each capturing visual information from a specific point. Computer processors are then used to stitch the information together to create images covering a 120-degree field of view with 5 times greater resolution than the human eye. David Brady led the work, published in Nature.
People have never had the feeling that when you look at a photograph that's better than being in a place. With this camera, you get certainly the feeling that you have telepresence because you'd see the same field that a human sees, but way beyond telepresence because effectively it's like you have binoculars. In the near term, I think that the applications of this will be for looking at wildlife refuges where you can see every bird in the sky. If you look at the Serengeti or some place where animals are everywhere, you can find all the animals. If we point this at the sky, we'll be able to see every meteor that hits the Earth and see everything dynamically happening in real time.
The calls learned by songbirds vary in response to noise in their environment. Publishing in the journal Biology Letters, Steve Nowicki from Duke University investigated how noise from nature and humans affects the calls learned by baby songbirds by raising 9 male swamp sparrow nestlings in a soundproof room and exposing them to recordings of song types sung by adult males of their species. The songs played were either clear or degraded. And when the birds matured and began to sing, the team found that only the clear recordings had been learned by the songbirds.
Young birds will preferentially learn to copy clear songs. They avoid degraded songs. The implication of that is that cultural evolution could very rapidly have birds shifting the way they sing to kinds of songs that are best adapted to transmit through an environment. Human changes in the environment, either by generating noise or by changing the habitat itself and how it affects transmission, can have a profound effect on the way birds sing.
And finally, the process of natural selection has been used to compose and refine pieces of music enjoyed by the masses. The website Darwin Tunes, which has been online since 2009, invited online users to listen to a range of short audio loops and rate them, with the highest ranking then combined to produce the next generation of sounds for rating again, resulting in over 2,500 generations analysed in their paper published in the journal PNAS. One of the more popular musical loops was each successive generation was found to create more recognisable and rhythmical versions of the tunes. Bob McCullum from Imperial College London led the work.
We know that in prehistoric times, music was passed on and copied from person to person and tribe to tribe many years ago. Now we tend to think of the composers being creative geniuses, and our results just point towards a greater role for the listener, show that the strength of listener selection is strong enough to produce listenable music.
And if you'd like to add to the next generations of music, which has now reached nearly 4,200, visit darwintunes.org.
Mira Sinthalingham with our Naked Scientists newsflash. You can find the transcripts and the references for all our news this week at our website, thenakedscientist.com/news.
Technology designed to monitor environmental pollution has been adopted by scientists to detect disease. The project by researchers at the University of Leicester, known as the Diagnostics Development Unit, has been likened to a Star Trek-style sickbay. At the moment, the equipment is under test at the Leicester Royal Infirmary. Planet Earth podcast presenter Richard Hollingham went along to the hospital's busy emergency department, where he met Tim Coates, Professor of Emergency Medicine at the hospital, and Paul Monks, who's the Professor of Atmospheric Chemistry at the University of Leicester.
We've taken instrumentation that we use in the laboratory and outside in the environment for actually smelling the air, sniffing the chemicals in the air, and we're now using it in the hospital environment to smell people's breath.
So what is the setup here? There looks like just computer monitors there, a camera stand, a tripod there. Now this, I recognise, this is a mass spectrometer, so you can analyse individual chemicals, a series of long metal tubes, complicated piping and the like.
Yeah, well, what you've got in front of you is what we call a proton transfer reaction time of flight mass spectrometer, but it's a way actually of measuring and weighing molecules very, very quickly. So we can take the molecules coming out of your breath and weigh them and actually look at the composition in terms of the chemical composition of your breath. And what we hope to be able to do with that is actually smell disease.
Now, Tim, we're in a room full of this equipment, but on the other side of this are the bays where there are patients coming in as we speak, being attended to in the emergency department.
That's correct, and we've got a series of ports through the wall here, both electronic and physical, so that the patient, the other side of the wall, can be monitored using the equipment in this room. Now that means that the doctors and nurses in the emergency department can continue treating the patient while the monitoring is going on. So even the sickest patients can be in there and we can be monitoring them. Now that's something in the past that's been really difficult to do. For example, a patient with a chest infection coming in, we know that different bacteria produce different molecules. We can sniff those molecules using the mass spec and perhaps tell which bacteria is in a patient's chest. Now that might help us give them the right antibiotic for their infection. We don't know that we can do that, but that's the sort of potential we're looking at.
What do patients do? What do you attach to them?
So they have a mouthpiece that they breathe in and out to get the breath sample. They also have a series of stickers that we put on the body. We have a series of cardiovascular monitors. So we're really looking at their heart with the cardiovascular monitors, their lungs with the breath analysis, and then we're also doing some imaging. You mentioned the camera and tripod. That's a hyperspectral imager, which has been translated across from space science. We're doing a battery of different tests on our patients.
What we really needed was a volunteer, so I agreed to try it out. The test involved breathing into a mouthpiece, a bit like an asthma inhaler, in time to a regular beep.
What you can see on the screen now as you're doing this is actually the CO2 in your breath, which is what we use as a marker. And then on the top is the volume of air that you're putting out into our instrument. And we can see on the mass spectrometer screen behind us the chemical data coming up from the measurements that we're making.
I must say I was pretty rubbish at breathing in time with a beep. That was quite difficult.
So now as we move over...
So we move over to the mass spectrometer, which is this shiny collection of tubes, and here's the screen with my breath analysed.
Yes, so we're actually looking at the chemicals in your breath, and we've looked at it in real time. And what we've got up on the screen here are peaks like acetone, which is a diabetic marker. Also ethanol, just to check that you haven't had a drink this afternoon before you came to join us.
So is that okay?
Yes, you'll live.
And for a hospital environment, this is a fairly fearsome bit of equipment. I imagine it's also very expensive. You really need to miniaturise this, don't you?
The idea at the end of the day is actually to miniaturise these things and maybe even produce handheld diagnostics. Something like the size of a glasses case that you'll be able to breathe into. Maybe even one day your mobile phone.
Paul Monks from the University of Leicester. You also heard Tim Coates from the Leicester Royal Infirmary. They were both talking with Richard Hollingham, and you can hear more in the latest Planet Earth podcast, which is available from thenakedscientists.com/Planet Earth.
Laying the facts bare. The Naked Scientists.
You're listening to The Naked Scientists with Chris Smith and with Helen Scales. And returning now to our theme this week of catching criminals in new ways using new technologies, fingerprints. Fingerprints have been used to catch criminals since at least 1858, and since then they have been the key to solving countless crimes. But some surfaces are hard to lift fingerprints from, especially if that surface has been cleaned or chemically altered in the interim. Now, researchers at Swansea University have developed a new technique to fingerprint some things that were previously unfingerprintable. Dr. Geraint Williams helped to develop the system, and he's with us now. Hello, Geraint.
Good evening, Chris.
So first of all, what actually, chemically speaking, is a fingerprint?
Well, I guess if you wanted to define what a fingerprint is, it would be the deposit that's left behind when the fingerprint ridges or the fingertip ridges, friction ridges, make contact with the surface. But compositionally speaking, there's a whole chemical cocktail in a fingerprint deposit. There are two parts to a fingerprint. There's the eccrine part, which is basically secretions produced by the eccrine glands in your fingertip. And that is basically sweat, but sweat is pretty complex on its own. Principally water, but it contains things like chloride salts of various metals, sodium, magnesium chloride, for example, things like urea, lactic acid, amino acids, etc. But there's also a second component. These are sebaceous deposits which are produced by sebaceous glands, not in your fingertip, paradoxically, but other parts of the human body. So, for example, in your face. So a person might touch their forehead or the side of their nose and pick up these sebaceous deposits, which are basically a whole cocktail of long-chain fatty acids and fats by themselves. So the fingerprint is actually made up of a real chemical cocktail, which is difficult to actually characterize.
So normally, if you dusted for prints, you'd be applying a chemical that would stick to those residues, and that's how you'd visualize it. But why then would some surfaces not be fingerprintable?
I guess if the fingerprint has changed, or if it's simply just made up of an eccrine deposit. So lots of the developers that are used to give you a high visual contrast between the fingerprint pattern and the surface on which it's deposited rely on the interaction of a developer with that sort of organic part, the fatty part of the fingerprint. So if it's missing, lots of these developers simply won't work.
So how does your approach differ?
Our approach differs from most conventional techniques in that it relies on measuring the interaction that the fingerprint itself makes with the surface on which it's deposited.
So talk us actually about your method. What does it involve?
It's an instrumental method. The instrument we use is called a scanning Kelvin probe, and it relies on scanning a very fine probe over the surface of interest. It doesn't actually touch the surface. And what it does is it measures a quantity called the Volta potential difference between the probe and the area of the sample directly underneath the probe. And that is an indicator of the chemical nature of that surface. So if, for example, a fingerprint deposit is on that part of the surface, then we'll have a considerably different voltopotential difference to a part which isn't in contact with the fingerprint deposit. And it's usually, what our technique is good for metallic or conducting surfaces and basically metals. And what the fingerprint does is the chloride salts in the fingerprint actually depassivate the metal, i.e. cause a small amount of corrosion to occur underneath the fingerprint deposit, and it's that actually small amount of corrosion that we actually pick up with our scanning Kelvin probe.
What happens when someone comes along and cleans the surface? Of course, if a corrosion event has occurred, that won't be wiped off then?
No, exactly. For example, if a criminal has been trying to cover his tracks by wiping off the fingerprints with a cloth, there is sufficient interaction of the chloride salts in fingerprint with the oxide film covering the metal for that chloride to be retained in that particular region, and it won't be wiped off physically.
What sorts of things are you using this for, or could this be used for, where present techniques just wouldn't cut it?
Well, the major items of interest to us are things like spent cartridge cases. They're notoriously difficult.
For guns, for example?
Yes, yeah, from serious crimes, gun crimes. And those pieces of evidence, so if, for example, there's a shooting and somebody's left some shell cases at the scene of the crime, typically it's almost impossible to lift any fingerprint detail from those pieces of evidence, providing maybe that the criminal has actually put his fingerprints on them to start with before they're actually fired. And that's because, obviously, when you fire a bullet, the casing is actually subjected to fairly high temperatures in the firing mechanism. There's also some contamination from blowback of the propellant, for example. There's also friction, the ejection mechanism, etc. So all these phenomena contrive to make it extremely difficult to actually give any kind of fingerprint visualization on that type of surface. But with the Kelvin probe, because most of the organic part of the fingerprint will be lost, for example, at the high temperatures which the casing will be exposed, the Kelvin probe gives you a fighting chance, because there's always a good chance that the chloride-rich deposits will still be there, because they won't be volatilized at those kind of temperatures.
Terrific. Geraint, stay with us, because we may have some questions for you. That's Geraint Williams from the Department of Engineering at Swansea University. You're listening to The Naked Scientists with Chris Smith and with Helen Scales. We're talking technology for catching criminals this week. Our guests, Dr. Graham Turnbull from St Andrews University, Pavel Matusek from Cobalt Light Systems, and Geraint Williams from Swansea University. I'll kick off with one for Graham. We've heard from Michael Malone on Facebook, nakedscientist.com/Facebook to take you to our page. I've heard about honeybees sniffing out explosives. Any updates on that, Graham?
Okay, yes. So as well as dogs, you can use other animals to find explosives, and bees are one of those. And so bees use several different cues to find food, including the smell of sources of food. And you can train them to associate the source of food with the smell of TNT. And so if you grab hold of a bee and pass TNT vapor across it, it sticks its tongue out. So this is an interesting new way of using animals in order to detect TNT, and there's a UK company called InSentinel that are developing this technology, biotechnology.
Thank you, Graham.
CB Axel on Second Life has a question I think we're going to throw to Pavel. Says, what is there to stop lots of terrorists each bringing a very small amount of liquid explosive and combining them when they're on the plane? Any thoughts on that, Pavel?
Well, the existing restrictions are meant to deal with such situations, because 100 milliliters is not to make a viable bomb. And obviously, any precursors for explosive would be detected by the instrumentation I was describing. So it's not just that explosives are detected, but also explosive precursors. So a list against which we are comparing the data is very comprehensive.
Thank you very much, Pavel. And Geraint, there's one here from Sven who says, could you remove fingerprints with sandpaper? Could you sand down those cartridge cases? We've got 30 seconds literally to answer this, please.
Yeah, I would guess you could. If you ablate enough of that surface, then you'll remove any kind of interaction. So the other one, of course, is to wear gloves when loading your shells.
We're putting ideas in the hands of criminals here. So basically, if you did actually scrape hard, you could erode the surface and then you wouldn't stand any chance of getting that.
That is correct, yes.
OK, thank you very much. Well, we'll have to leave it there because we're pretty much out of time for those questions. But there is one very hard question left to answer this week, Hannah.
Indeed. Now, sleuthing after the answer to a crime-inspired question of the week, here's Hannah Critchlow.
The Naked Scientist's Question of the Week, brought to you in association with the Houter Wisman Foundation, supporting science and education from Alpha to Omega.
This week we find out if we can use clever gene therapy tricks to escape detection at a crime scene.
My name is Rick Santiago and I live in Rio de Janeiro, Brazil. Imagine that a criminal knows that he runs the risk of leaving some incriminating material like hair or blood in a crime scene. Would he be able, by means of genetic therapy, to change the inner layer of the mouth to prevent that any cells that he left on the crime scene will still match his inner cheek cells?
We asked Dr. Paul Debenham, Director of Innovation and Development at LGC, the company that provides forensic tests for police across the UK, and he said,
"The possibility proposed is of some sort of sci-fi mouthwash which is able to transfer false DNA profile sequences into your mouth cells. To achieve an efficient DNA transfer, one would need to piggyback the DNA profiling sequences into a human virus to achieve infection of the mouth cells. Doesn't sound the sort of treatment many people would volunteer for. This treatment will not destroy the existing person's DNA in their mouth cells, so one would expect to see evidence of a multiple DNA profile and immediately suspect something strange was afoot. Current profiling methods can indicate the presence of more than one source of the DNA when the minor component is of the order of a few % of the major component. There are many technical caveats to that ratio, but that's a ballpark figure that people can work with. If such a mouthwash technique ever became possible, then I could imagine that the sampling procedure deployed would just change to swabbing from a skin surface, plucking out hair roots, or the use of blood. Just a pinprick would suffice.
So, even if only a few % of your own DNA was left in your cheek, DNA fingerprinting is so sensitive that it would still pick up the real you. But what about grafting tissue containing someone else's DNA onto your inner cheek? We asked Surrey University oncologist Professor Hardeep Panda.
If you do that, the take-up of the cells is incredibly inefficient, wouldn't last very long, and would most likely be sloughed off or rejected because they'll be from a different genetic background. So it's a nice idea, but I think this is one that won't be a problem for the police forensic folks.
So, rather than trying to change your own DNA, we think that a better way to outwit the justice system would be to deluge the crime scene with other people's DNA, for instance by emptying the contents of a vacuum cleaner bag into the area. Now, moving on, let's hop, skip and hope not to crash into next week's question.
My name is Colin McKenzie. I'm a retired family physician living in Santa Cruz, California. The use of ice and ice packs and even ice machines circulating ice water over injured parts of the body is increasingly popular in the treatment of all manner of soft tissue injuries and post-surgical events, including hip and knee replacements. I don't understand the physiological rationale of such treatment. Is there any evidence, other than anecdotal, of the benefit of such treatment?
So does the myth that ice can reduce injury swellings hold true? And if so, how? Send your thoughts to Chris at thenakedscientist.com, tweet at Naked Scientists, write on our Facebook page, or join in the debate on our forum, which is at nakedscientists.com/forum.
And that was Hannah Critchlow.
Well, that is all we have time for this week. I'll leave you with a thought from Second Life, where Dally Waverider says he's now, based on what we were discussing with honeybees, imagining angina patients being chased by swarms of the things. That is it for this week. Join us next time for Crowd Science. Millions of people will be attending the London Olympics, so are we risking triggering a pandemic? And how have the venues been designed to make sure people can escape safely in the event of other kinds of emergencies? Meanwhile, thank you very much this week to Graham Turnbull, Pavel Matasek, Sinan Arul and Geraint Williams, and also to our producer this week, Ben Valsler. If you have a question for us in the meantime, then you can send it to Chris at thenakedscientist.com. You can tweet at Naked Scientists or go to facebook.com/thenakedscientists and leave your points and comments there.
The Naked Scientists podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the STFC, the Natural Environment Research Council, and UK FAST. For more cutting-edge science, join us online at nakedscientists.com.